So we'll solve for the slope or the rotation at the left end of the beam. So all the way over here at the pin over there. E and I are going to be constant. We obviously have like an L-shaped, sort of a funny shaped beam here. And this is the location that we're interested in solving for something. So let's go ahead and look at how would we use superposition to solve this. And so previous week we would have broken out the beam equation. We'd have done some statics. We would have found the internal moment as a function of x and started integrating between those 2 points, the pin and the roller. And so we've got this table, this deflection table, that we want to try to utilize. And so what we're going to do is find this beam actually in the deflection table in Appendix D. So we're going to break this determinant structure. How do we know it's determinant? We've got 2 external support forces by a pin. We have 1 from a roller. That gives me 3 external support forces. So I have 3 external unknowns. I have 1 free body diagram that would give me 3 equations of equilibrium. And so I end up with determinant because they are properly posed. So I am going to use determinant superposition. So the first piece I am going to analyze is just the piece between the pin and the roller with the distributed load present. And so we just have a simply supported beam over 10 feet with 2 kips per lineal foot on it. So that one is going to be in the deflection table. Let's just go ahead and scan down to it. And we've got our case number 6 down here. That would be the exact same picture. So we've got some ability to find the slope at the end right there, either end. We're going to use the left end, so we will end up using that value, and we'll determine if it's positive or negative based on the deflected shape. And so we've got now left over, we've got a beam sitting here, and we've got an applied moment all the way down there at the bottom. And that applied moment has the effect of an applied moment anywhere on the structure from a statically equivalent perspective. And so we are going to choose to preserve that segment, that simply supported segment, and we are going to draw a statically equivalent representation of that force right up here at the roller. And that statically equivalent representation is just going to be a 10 kip-foot moment. No force will be present, no statically equivalent force results. And so I've got now a 10-foot beam with a 10 kip-foot applied moment. That also is in the table. That's going to be case 7. So let's go down and take a look at it. There's a simply supported beam with a moment at the end. And we've got a couple choices over here for theta, the rotation at an end, either at A or B. And so we're going to end up using the rotation at A at the far end, the end away from where the moment is applied. So we're going to end up using ML over 6 EI. So let's go back up here and let's start to calculate the deflection at the pin. So we have a negative WL cubed over 24 EI. How do we know it's negative? What I'm going to do is draw the deflected shape. Right, if the beam acts, it's going to deform the system to this shape. And so the slope over here at A is going to have a negative value. So I'm going to use negative WL cubed over 24 EI. And I can go ahead and plug in some of the values that we've got. 2 for W, L is 10. E and I are going to be constant, so they will carry along in the problem. So there's my answer for theta at the pin in structure 1. Beta at the pin. Over on structure 2, we have a simply supported beam with an applied moment at one end. It's going to cause our beam to have a negative moment or an unhappy face. If we went ahead and cranked moment into the right end, we would end up with a slope over at the left end that would be positive, and that's why we're going to choose plus ml over 6EI. We plug in some of our values. L is 10. The moment is 10 kip feet over 6EI. And then all I'm going to do is add those two numbers together. I'm going to add theta at the pin in structure 1 plus theta at the pin in structure 2. And by superposition, that will get me theta at the pin in the actual structure. So my total slope is going to be minus 66.6 kip feet squared over EI, or that would mean a negative slope, and I would give the value of the rotation and show a picture of it rotating clockwise.